Scientists find that dark matter, shown here in black, was essential to forming the large-scale structure of today's universe. This computer simulation traces how cosmic structure evolved over time. The bright knots contain thousands of galaxies drawn together by the vast sheets and tendrils of dark matter. These knots grew from the densest regions seen in the cosmic background radiation. The less dense regions of the background became cosmic voids, big, empty bubbles, hundreds of millions of light years wide. The gravity generated by normal matter is much too weak to create this cosmic web. Dark matter must be doing the job. What is dark matter? Scientists are conducting experiments to find out. Some of their detectors are buried deep beneath Earth's surface to minimize interference. One detector, mounted on the International Space Station, looks for signs of dark matter particles interacting far across the galaxy.
The EMS experiment on the ISS was designed to find a specific type of dark matter, one that could explain our observations, and after 2 years of operation, it published a result. That type of dark matter simply doesn't exist. It's a big hiccup in the research being done, but that's the nature of science. Dark matter is an elusive substance. The only way that we can look for it is to think of every form that it could take, then build experiments that might be able to find those forms or prove that they don't exist so that we can move on to the next possibility. We have to go to these extremes because of how difficult dark matter is to detect. It's called dark matter, but it might be more accurate to call it invisible matter. Nearly all observations that we make in astronomy involve the electromagnetic spectrum. We look at visible light, radio waves, X-rays, and so on, but dark matter doesn't interact with any of the parts of this spectrum. It doesn't shine, reflect, or scatter light, so we can't utilize our usual toolbox to detect it. In the past, one of the leading candidates for dark matter was something called a massive compact halo object, or MACHO for short. MACHOs were thought to be massive objects that were composed of normal matter that still interacts with light, but doesn't emit much light. These could be objects like failed stars, black holes, or large planets. However, over the past few decades, very careful surveys have found that there aren't enough of these objects to account for the predicted amount of dark matter in places like out here, at the edge of our galaxy. So if dark matter is not a MACHO, then what is it? Another competing model is still being pursued. What if dark matter was made of small particles that don't interact with light and usually pass through other atoms? This particle model was dubbed a WIMP, for weakly interacting massive particle, and that would be something that we could actually search for here on Earth. Even though they're called massive, such particles would be tiny compared to the planetary or even the human scale. Many Earth-based detectors are trying to get a signal from some type of WIMP. Different detectors are made to test different hypotheses of what the WIMP might be. The LUX experiment uses an ultra-dense fluid of liquid xenon located in an abandoned gold mine to shield it from other particles. They're looking for anomalous signals from dark matter particles interacting with the xenon, which would release ultraviolet photons as a result of interacting with a WIMP. So far, we've only received null results, but that's actually helping to further narrow down our search. Some scientists propose that maybe dark matter particles never get close to our planet and instead are only found in farther regions, like at the edges of galaxies. If that's the case, maybe we can't sit around waiting for dark matter to come to us. Maybe we need to make some for ourselves. Since dark matter shaped the early universe, it likely originated at the same time as observable matter. The Large Hadron Collider, which crosses the French and Swiss border right around here, accelerates particles to high speeds that recreate some of the interactions that likely occurred in the early universe. Scientists are trying to see if they can learn more about this early age and maybe even make a dark matter particle. So far, learning about dark matter has been confounded by its indirect interaction with light, since light is overwhelmingly the major way that we learn about the universe. Recently, however, new results from a gravity wave detector have opened a new window into the universe. LIGO, the Laser Interferometer Gravitational Wave Observatory, was able to detect gravity waves coming from two colliding black holes. That bloop was the sound of that observation, and it earned the team that first heard it a Nobel Prize. Just the other week, LIGO was able to detect the collision of two neutron stars early enough for over 70 Earth and space-based observatories on all 7 continents to observe the phenomenon. We know that dark matter interacts with gravity, and while it's still too early to say anything with certainty, the LIGO result might be the beginning of a new type of observatory, one that can sense dark matter directly. LIGO is huge, with the distance between the interferometers, the individual observing parts of the larger observatory located here and here, spanning over 3,000 kilometers. But the next generation of gravity wave detectors will be more sensitive and even larger, enabling us to go from where we are now with our detections of the waves to being able to use them to better understand our universe. Among those, ELISA is proposed to launch in 2034. It would be similar to LIGO, but much, much larger. This would be a gravitational wave space observatory on a whole different scale. ELISA hasn't yet been launched, but in this case, a single interferometer arm would stretch over millions of kilometers in outer space, not just a few thousand here at home. Unfortunately, due to the time frame, we'll have to wait a while to see the data from it. But even after we eventually figure out dark matter, there may still be so much about our universe that we just don't know, let alone understand. In fact, as we've explored further, we've found that there are parts of our universe even more mysterious than dark matter.
While scientists expect that dark matter particles may soon be found, another mystery has emerged that's changing how we think about the future of our universe. Astronomers had thought that the gravity exerted by all the matter in the universe would slow down the rate of cosmic expansion. To check this prediction, teams of observers charted the distances and speeds of extremely remote galaxies by studying exploding stars called supernovas. As this time-lapse view of the Milky Way shows, stars explode fairly often, at a rate of about 2 per century in a galaxy like ours. So, if you observe enough galaxies, you can spot a new supernova every few nights. The observers were especially interested in a particular type of supernova, like this one, where the corpses of 2 dead stars orbit each other so closely that they eventually collide and detonate. Such supernovas are very bright and consistent in brightness, providing scientists with an extraordinary tool for measuring cosmic distances across the universe and back through time. By measuring the distances and speeds of hundreds of supernovas, the astronomers learned how fast the universe was expanding billions of years ago. By 1998, to their astonishment, they found that the universe hadn't expanded faster in the past as expected. Just the opposite. It used to expand more slowly than it does today. The expansion rate isn't slowing down, it's speeding up, accelerating. And it's been accelerating for the past 5 billion years. The pressure causing the acceleration is called dark energy. But that's just a label. Nobody yet understands dark energy, though it appears to be powerful enough to shape the course of cosmic destiny. Matter and energy are two sides of the same coin, as Einstein revealed in his famous equation, E equals mc squared. In those terms, dark energy weighs in at nearly 70% of the total stuff of the universe. Dark matter accounts for almost all the rest. Normal matter, all that we are, or all that we've ever seen or touched, amounts to less than 5% of the known universe. So we know precisely when the universe began, and we're beginning to understand what it's made of. But how big is it? Our observable universe is limited to the part of the cosmos from which light has reached us here on Earth. But every galaxy occupies the center of its own observable universe. Observers in this distant galaxy can see light from regions we cannot yet see. And we can see regions they cannot see. So no matter who or where you are, you'll reach the same conclusion, that the universe as a whole must be bigger than the part of it you can perceive. How much bigger? Some scientists speculate that if the observable universe were the size of a planetarium dome, the entire universe would be larger than planet Earth. Others suggest it may be infinitely large. Clearly, there's more to the universe than meets the eye. The Big Bang happened long ago, but not far away. It happened here, there, and everywhere. Peering into the dark, we stand on the threshold of great discoveries. And we always will, as long as we keep exploring.
As the lights come up and as you get ready to go, please make sure to check the area around, between, and below your seats. Please make sure that all of your belongings, everything that came in with you, goes out with you. Please also keep in mind that the exits are located at the top of the stairs, so make your way up, not down. However, should the stairs pose an issue for you for any reason, please remain seated until everyone else has safely exited the theater, and a staff member will be by shortly to escort you to a lower exit. If you have any quick questions, I'd be more than happy to take them up in the pilot's booth in the back. I'll try to answer any questions I get to the best of my abilities. Once again, my name is Dash, and on behalf of myself and the Morrison Planetarium team,